Heat treating is a group of industrial and metalworking processes used to alter the physical, and sometimes chemical, properties of a material. The most common application is metallurgical. Heat treatments are also used in the manufacture of many other materials, such as glass. Heat treatment involves the use of heating or chilling, normally to extreme temperatures, to achieve a desired result such as hardening or softening of a material. Heat treatment techniques include annealing, case hardening, precipitation strengthening, tempering, normalizing and quenching. It is noteworthy that while the term heat treatment applies only to processes where the heating and cooling are done for the specific purpose of altering properties intentionally, heating and cooling often occur incidentally during other manufacturing processes such as hot forming or welding. Physical processes. Metallic materials consist of a microstructure of small crystals called grains, or crystallites. The nature of the grains is one of the most effective factors that can determine the overall mechanical behavior of the metal. Heat treatment provides an efficient way to manipulate the properties of the metal by controlling the rate of diffusion and the rate of cooling. Within the microstructure, heat treating is often used to alter the mechanical properties of a metallic alloy, manipulating properties such as the hardness, strength, toughness, ductility, and elasticity. There are two mechanisms that may change an alloy's properties during heat treatment. The formation of martensite causes the crystals to deform intrinsically, and a diffusion mechanism causes changes in the homogeneity of the alloy. The crystal structure consists of atoms that are grouped in a very specific arrangement, called a lattice. In most elements, this order will rearrange itself depending on conditions like temperature and pressure. This rearrangement, called allotropy polymorphism, may occur several times at many different temperatures for a particular metal. In alloys, this rearrangement may cause an element that will not normally dissolve into the base metal to suddenly become soluble, while a reversal of the allotropy will make the elements either partially or completely insoluble. When in the soluble state, the process of diffusion causes the atoms of the dissolved element to spread out, attempting to form a homogeneous distribution within the crystals of the base metal. If the alloy is cooled to an insoluble state, the atoms of the dissolved constituents may migrate out of the solution. This type of diffusion, called precipitation, leads to nucleation, where the migrating atoms group together at the grain boundaries. This forms a microstructure generally consisting of two or more distinct phases. Steel that has been cooled slowly, for instance, forms a laminated structure composed of alternating layers of ferrite and cementite, becoming soft pearlite. Unlike iron-based alloys, most heat-treatable alloys do not experience a ferrite transformation. In these alloys, the nucleation at the grain boundaries often reinforces the structure of the crystal matrix. These metals harden by precipitation, typically a slow process, depending on temperature. This is often referred to as age hardening. Many metals and non-metals exhibit a martensite transformation when cooled quickly. When a metal is cooled very quickly, the insoluble atoms may not be able to migrate out of the solution in time. This is called a diffusionless transformation. Quote, when the crystal matrix changes to its low-temperature arrangement, the atoms of the solid become trapped within the lattice. The trapped atoms prevent the crystal matrix from completely changing into its low-temperature allotrope, creating shearing stresses within the lattice. When some alloys are cooled quickly, such as steel, the martensite transformation hardens the metal, while in others, like aluminum, the alloy becomes softer. Effects of composition. The specific composition of an alloy system will usually have a great effect on the results of heat treating. If the percentage of each constituent is just right, the alloy will form a single, continuous microstructure microstructure upon cooling. Such a mixture is said to be eutectoid. However, if the percentage of the solute varies from the eutectoid mixture, two or more different microstructures will usually form simultaneously. A hypoeutectoid solution contains less of the solid than the eutectoid mix, while a hypereutectoid solution contains more. Eutectoid alloys. A eutectoid alloy is similar in behavior to a eutectic alloy. A eutectic alloy is characterized by having a single melting point. This melting point is lower than that of any of the constituents, and no change in the mixture will lower the melting point any further. When a molten eutectic alloy is cooled, all of the constituents will crystallize into the respective phases at the same temperature. A eutectoid alloy is similar, but the phase change occurs not from a liquid, but from a solid solution. Upon cooling a eutectoid alloy from the solution temperature, the constituents will separate into different crystal phases, forming a single microstructure. A eutectoid steel, for example, contains 0.77% carbon. Upon cooling slowly, the solution of iron and carbon will separate into platelets of the phases ferrite and cementite. This forms a layered microstructure called pearlite. Since pearlite is harder than iron, the degree of softness achievable is typically limited to that produced by the pearlite. Similarly, the hardenability is limited by the continuous martensitic microstructure formed when cooled very fast. Hypoeutectoid alloys. A hypoeutectic alloy has two separate melting points. Both are above the eutectic melting point for the system, but are below the melting points of any constituent forming the system. Between these two melting points, the alloy will exist as part solid and part liquid. The constituent with the lower melting point will solidify first. When completely solidified, a hypoeutectic alloy will often be in solid solution. Similarly, a hypoeutectoid alloy has two critical temperatures, called arrests. Between these two temperatures, the alloy will exist partly as the solution and partly as a separate crystallizing phase, called the proeutectoid phase. These two temperatures are called the upper and lower transformation temperatures. As the solution cools from the upper transformation temperature toward an insoluble state, the excess base metal will often be forced to crystallize out, becoming the proeutectoid. This will occur until the remaining concentration of solutes reaches the eutectoid level, which will then crystallize as a separate microstructure. A hypoeutectoid steel contains less than 0.77% carbon. Upon cooling a hypoeutectoid steel from the austenite transformation temperature, small islands of proeutectoid ferrite will form. These will continue to grow and the carbon will recede until the eutectoid concentration in the rest of the steel is reached. This eutectoid mixture will then crystallize as a microstructure of pearlite. Since ferrite is softer than pearlite, the two microstructures combine to increase the ductility of the alloy. Consequently, the hardenability of the alloy is lowered. Hypoeutectoid alloys. A hypoeutectic alloy also has different melting points. However, between these points, it is the constituent with the higher melting point that will be solid. Similarly, a hypoeutectoid alloy has two critical temperatures. When cooling a hypoeutectoid alloy from the upper transformation temperature, it will usually be the excess solutes that crystallize out first, forming the proeutectoid. This continues until the concentration in the remaining alloy becomes eutectoid, which then crystallizes into a separate microstructure. A hypoeutectoid steel contains more than 0.77% carbon. When slowly cooling a hyper-eutectoid steel, the cementite will begin to crystallize first. When the remaining steel becomes eutectoid in composition, it will crystallize into pearlite. Since cementite is much harder than pearlite, the alloy has greater hardenability at a cost in the ductility. Effects of time and temperature. Proper heat treating requires precise control over temperature, time held at a certain temperature, and cooling rate, with the exception of stress relieving, tempering, and aging. Most heat treatments begin by heating an alloy beyond the upper transformation temperature. This temperature is referred to as an arrest because at the A3 temperature the metal experiences a period of hysteresis. At this point, all of the heat energy is used to cause the crystal change, so the temperature stops rising for a short time and then continues climbing once the change is complete. Therefore, the alloy must be heated above the critical temperature for a transformation to occur. The alloy will usually be held at this temperature long enough for the heat to completely penetrate the alloy, thereby bringing it into a complete solid solution. Because a smaller grain size usually enhances mechanical properties, such as toughness, shear strength and tensile strength, these metals are often heated to a temperature that is just above the upper critical temperature, in order to prevent the grains of solution from growing too large. For instance, when steel is heated above the upper critical temperature, small grains of austenite form. These grow larger as temperature is increased. When cooled very quickly during a martensite transformation, the austenite grain size directly affects the martensitic grain size. Larger grains have large grain boundaries, which serve as weak spots in the structure. The grain size is usually controlled to reduce the probability of breakage. The diffusion transformation is very time-dependent. Cooling a metal will usually suppress the precipitation to a much lower temperature. Austenite, for example, usually only exists above the upper critical temperature. However, if the austenite is cooled quickly enough, the transformation may be suppressed for hundreds of degrees below the lower critical temperature. Such austenite is highly unstable and, if given enough time, will precipitate into various microstructures of ferrite and cementite. The cooling rate can be used to control the rate of grain growth. It can even be used to produce partially martensitic microstructures. However, the martensite transformation is time-independent. If the alloy is cooled to the martensite transformation temperature before other microstructures can fully form, the transformation will usually occur at just under the speed of sound. When austenite is cooled slow enough that a martensite transformation does not occur, the austenite grain size will have an effect on the rate of nucleation, but it is generally temperature and the rate of cooling that controls the grain size and microstructure. When austenite is cooled extremely slow, it will form large ferrite crystals filled with spherical inclusions of cementite. This microstructure is referred to as spheroidite. If cooled a little faster, then coarse pearlite will form. Even faster, and fine pearlite will form. If cooled even faster, bainite will form. Similarly, these microstructures will also form if cooled to a specific temperature and then held there for a certain time. Most non-ferrous alloys are also heated in order to form a solution. Most often these are then cooled very quickly to produce a martensite transformation, putting the solution into a supersaturated state. The alloy, being in a much softer state, may then be cold worked. This cold working increases the strength and hardness of the alloy, and the defects caused by plastic deformation tend to speed up precipitation, increasing the hardness beyond what is normal for the alloy. Even if not cold-worked, the solutes in these alloys will usually precipitate, although the process may take much longer. Sometimes these metals are then heated to a temperature that is below the lower critical temperature, preventing recrystallization, in order to speed up the precipitation.